those are the real high-frequency transmission lines. The series, you can make the theory to all the theory we discussed in chapter 2, the transmission line series. Okay? So all the picture is like in chapter 2. In chapter 2, we are talking about the general any ideal case or some of the different cases we're talking about a lossless and a lossy transmission line, right? General transmission line theory. Okay. And in chapter 3, we are going to map, okay? Map the theory in chapter 2 to 3 kinds of the real or maybe practical or different industrial. You can see the physical transmission line. We have already discussed about the coaxial cables. And today we will discuss something about the microstrip lines. And for the rest of the class, we will go to discuss some fundamental knowledge of the waveguide. Okay, those are 3 real transmission lines in chapter 3. In chapter 2 is ideal, a general case. Okay, before we start, I'm going to ask you the questions. Are you late? So you are late. And Wu Show is late. Cai Weixiang not yet. Okay. Who else? I didn't call your name. Okay, you are late. So Yu Qijun. Because of rain. Because of rain. It's a bad habit. Getting late. Okay, Zhang Zejia, you late? When did you come? After I call your name, right? Okay. Zhong Bingjun also late, right? 何伟丽 haven't show up yet. 蔡伟翔 haven't show up yet. 曾子轩 not yet. So I will ask you a question. If you give me the answer I want, I will give you extra point. Okay. Okay. Wu Wenxiu. Okay. Your opportunity. Question. So what are in chapter 2, what is the most important? What are those most important parameters? We talk about the general transmission theories. How do you describe the transmission line? Give me a parameter I didn't write down on the general transmission line. Give me one of the unknown to describe. Okay, great. Very good. So Z0, okay, you can get an extra point, easier. But you don't need it actually. It's a very high score for the entertainment. Okay, who will show? How about the second one? Okay, Cai Yueting. Give me another. Yes. Very good. Okay, and I think for to describe a transmission line, the parameter Z0 and beta is good enough because after that you describe this transmission line, you can use this parameter to transfer to other parameters you need. Okay. We also need a physical definition of transmission line. Let me ask about this one. So Yu Qijun, yeah, give me another parameter to describe a transmission line. What else? L is great. Okay, you can also earn the good point because I do this again and again and again. Can you tell me what is L? Huh? What is that? I know you understand, but you need to give me the answer. What is that? Long, short, yes. So what is the name of that? Long and short. Okay, in Chinese, what's that? Yes, okay. In English, we call that L means length. And also, it is a physical length. How long it is in physics, physically, exactly how many millimeter, how many centimeter, how many meters. Okay, this is it. And this is how we describe. Okay, the question is getting harder and harder. Okay. This is what we learned from chapter 2. According to these parameters, and the ZL is, it depends on what is the load. This transmission are connected to something outside. So only these three parameters are determined by our high frequency transmission line. We agree, right? Okay. So, more. For the coaxial cable, Zhang Zuren, what is the mode for coaxial cable? Yes, mode. I mentioned that many times. But I haven't explained yet, so maybe this is a difficult question to you, right? Because you didn't pay attention. Because I never explained what is the mode. M-O-D-E. What kind of the mode of your electrical and the magnetic field propagating on your coaxial cable, or maybe you say inside the coaxial cable? What is the mode? Okay, you can pass. Maybe I will come back to ask you maybe easy question later. Okay, you don't have a quick answer right now. Okay, it's fine. How about Wang Bochen? Yes, can you explain this one? Mode. For the coaxial cable, what is the mode of the coaxial cable? Can you write down it, please? No? Okay. Let me ask about Xu Yongsen. You want to
TM mode.
Yes, that's great. I know you want to answer. TEM mode. Okay, remember it's important. If your transmission line is using TEM mode, your answer is easy to calculate, to be calculated. Okay, answers are very easy to be calculated. Are very easy. Okay. Okay. I will explain what is TM mode maybe next week. Okay. Maybe next week. Okay. Just hold. Just be patient. Hold on.
在 TV 的那里是那个跟横向
Yes. Yes. But
那个就是地方波导。
yes. Yes. That's why I say I will explain next week. Yeah. Because of that, I think
陈子轩
late. Very late. Okay. So more. Chen Jinxuan. Next. For coaxial cable TM mode, you can use the series we have been told in chapter 1. What is the equation to obtain the phase velocity? What is the velocity of TM mode? dP equals to, you remember that? If you don't have a quick answer, maybe you can just say pass.
Omega over K.
Yes, that's great. That's great. So beta is the propagation constant, or maybe equals to K, right? K is the wave number, and the beta is your propagational constant. Okay, it's great. So this is a professional question, so you can answer. Okay, for TM mode, you can use this equation. It's nice. How about 选离婚菜? Okay, one more question. Give me another equation of the phase velocity. You have learned before. What is Vp? Vp equals to except omega over beta. Give me another.用中文讲也，人家写也可以。Okay, either way. Okay, I'm here. Give us the answer. Very good. Good time. 曾子轩 your turn. What is phase velocity again? Give me another answer if we know the material has the epsilon r. Epsilon r. We know epsilon r. Can you transfer this equation to some other form? I want you to use an equation with epsilon r, you know the material. Don't have an answer? You can just pass it. Fine, I can ask another student. You want to try? This is a review. This is a review of chapter 1, right? What? Do you have an answer? No? Yes? Do you want to try? So 2 pi over omega equals to 1. You sure? Sorry, it's not the correct answer. Right? This is true. So 2 pi over omega is 1, right?
Yeah.
But no. Okay. Okay, at least you try. But just next time, just give me a right answer. Chen Jiayi, can you give me an answer for another equation of Vp using epsilon r? You want to try?
But no, I don't see the
I think it's okay. Write it down. Write it down. Maybe you want. This is the answer. I want some equation with epsilon r. Okay, thanks. But it's later. This is not correct. This is not. This okay. We explain this later. Okay. Explain this later. Okay. So who is the next? Cai Xinjun. Can you use the review? You cannot get rid of it if you don't understand. I will ask you again. They will come back to find you until you understand. No? Okay. Who's next? Zhang Weiteng. You know the answer? I think you answered the same question before, right? Maybe you have the right answer before, but I don't know if you still remember. Why? Yeah, yes. Okay, so Vp equals to, you want some calculation, huh? Are you sure? Okay, then equals to, don't be nervous. Yeah, it's correct. That's the answer I want. But it's ugly. Why ugly? Can you simplify epsilon r? No? I see you are nervous. Come here. Give me your pen. Epsilon r equals to square root, what's your equation? Vp. Solve the equation for Vp. Try to use the big whiteboard. Let No, don't look at that. Just use this. Okay. I see you are nervous. Okay, so VP equals to okay, that's it. Please change your answer. Yes, this is the question. The answer I want. I don't know what you are thinking about. Find out. Okay. Okay, two more questions we need to know. They are the same. So I erase one of it, okay? K equals to beta, right? For T and O. And actually this is what I want. So they are the same because square root mu epsilon equals to the epsilon r multiplied divided by c. Actually, this is the same. So I keep only this part. So this equals to this is actually only information I need. Okay. This is for the TEM mode, but for coaxial cable, I use different color. Somebody can help me to copy what is the average L and the average C. No, let me just ask. Average inductance and average capacitance. So who is the next? Li Guanyi, give me L, okay? And Zhong Tingjun, give me C. Do you know where the answer is? You know, come here to write down. The average inductance and the average capacitance in the beginning of chapter 2. Okay, please. Okay, good. Continue. Do you know answer? No? Okay. On the cheek. Do you know answer? Write down. Tell me to write down. Let me, okay, you can just use let me use the parameters we usually use, okay? This one, I change that to epsilon 0 and epsilon r, they are the same. And for this one, it's mu 0, okay? I think everyone understand, okay? What are those equations if for beta and characteristic impedance, if we use average inductance and C for the lossless transmission line? Beta equals to Zhang Zhejiang, did you answer yet? No? Okay. Beta equals to, those are in our quiz, right? Remember? What is the beta of the coaxial cable if we use an L and a C? Remember your quiz? You want to answer? Yeah. Notice I use different color to separate different things, okay? They have some meaning. So beta equals to, okay, that's good. How about Z0? Zhang Youyu, do you know Z0? No? For coaxial cable, remember? In quiz, do you remember your quiz? I already gave you a quiz about this question. This is just a review. Quiz, do you remember? Okay, try it. Yeah. Good. Avi, come help. Can you just do this together? Just put this inside. I think we did that before, right? Well, help. Using this too hard. There's no hard. And I already called everyone. So you are next one. That's why I want you to answer all the questions. All the rest of the questions I want. Just put the blue part inside the orange part and you get an answer. And this is what we did for the quiz, right? Remember, everyone? Remember the quiz? If you forget, go to my website or check your quiz. you use these two relationship? You guys know these two, right? This is speed of light. And this is theta, the impedance, wave impedance in the air. Can you use these two parameters instead of mu0 and epsilon 0? Can you do that? You guys know these two equations, right? They are just the constants. The square root. How about beta? Beta use this one for beta. Number sum. Okay, thank you. Okay, I need to emphasize that this is the average capacitance but this is the speed of light. They are different. Okay, this is speed of light. Don't mix that up. This is a small one. Okay, and that is the average capacitance. They are different. This is large C, capital C, and this is small c. Okay, I try to review everything I've taught. I just write it together on your whiteboard. Okay, for just only in the coaxial cable. So for Z0, let me reduce it. Okay, this is a coaxial cable. Coaxial cable has the average inductance and the average capacitance. That's why for the coaxial cable, your characteristic impedance is, just go to the result. It is 2 pi and the natural log d over a and eta 0 over square root of epsilon r. Okay? And I don't need this. And look at that. The beta. If I do this one, I found beta equals to omega over c multiply epsilon r. This relationship is totally the same as what we found here, right? You use two different ways, you get the same result, right? Did you see that? For the equation here, it's the same as the equation here. So, you don't need that. They are the same, so I don't need. So I have the result, this one and this one called cohesion table. Are we good? Understand? I try to simplify because it is TEM mode. So we can do that. Next, I will give you more opportunities for students haven't answered my question yet. Okay, this is the coaxial cable. CABLE. This is what we learned last week. Remember, huh? And maybe a couple of weeks ago. Microstrip lines. Okay. I think everyone knows microstrip line except Wu-Wen-Xiao line. Give you gift. If anyone you don't know microstrip line, come here to ask Wu-Wen-Xiao. This is the microstrip line. This is the line I always draw. So did you see that? Okay. Gift. So this is the line we are talking about. It is the primary issue we discussed today. Okay. I can draw it up for the physical dimension, but maybe later. Let me ask one more question first. So, Wu-Wen-Xiao 蔡约宁、于其俊 answer right? You correct right? 于其俊. Okay. So, Zhang Zhuren, you haven't right yet, right? Okay. Well, again, it's coincidence. You are so lucky. What is the mode for microstrip line? Okay, good. Tell me. You question here and also question TE mode or TM and the TM microstrip line. I am very sorry to tell you that. Okay, now you learn, huh? Because that's why you learn. Huang Bochen, yeah, okay. This one? Okay.
Almost.
Okay. Chen Jinxun, you answer right. You already got the right answer. Li Kunchen, you already got the right answer. Okay. Zhen Zixuan, your turn. What is the mode for microstrip lines? Do you know that? If you don't know, just tell me you don't know. I will just ask. No. Okay. Chen Jiayi, did you write? Did you get? Do you want to answer? TM. Are you sure? If that's the same, I don't need to write it down. That's why I need to write. I need to write down. Huh? Yeah, this is the answer. Write down. Yeah. Okay, good. Fine. But if you are semi-correct, okay, good. So, yes. Okay. You got right answer. Okay. Let me write down again, okay? Your answer is correct. but I want to keep the capital, So let me write down. This is quasi-TEM mode. What does quasi mean? Abi, help us. Do you know quasi? It's an English term. Do you know or not? Do you know? You don't know quasi? Okay. You know? Huh? No? Okay. Okay. Quasi means approximation. It's close, but it is not. Understand? Quasi, it's very close. It is approximation, approximately. Very similar, but not. Not. It is not TEM, but looks like a little bit like TEM, but not TEM. Okay? You can check your dictionary about quasi. Okay? Quasi is. Okay? Now everyone learn the word quasi-TEM mode. Quasi. Okay? Next. Okay. So, this quasi, as I say, it is close. Now it's new. Something new. This is, okay. Why I need to review everything? Why do I need to do that? Because I want to explain quasi. You know coaxial. If you don't know everything from here, that's your homework. You need to try to review it. Don't forget. We spend so much time to study chapter 1, chapter 2, and coaxial cable, right? Don't forget about that. I try to use coaxial cable theory, which is in TEM mode, try to tell you a new transmission line, microstrip line, which is quasi-TEM mode. For the quasi-TEM mode, now it's new, so no more question. VP is also equals to omega beta set, but equals to speed of light over divided by the square root of epsilon E. This is why I tell you it is quasi. You have the material, you know the material, the epsilon R of your FR4 is 4.2. But your VP is not C over square root of 4.2. It is a square root of epsilon E. What is epsilon E? It is a effective dielectric constant. It is not epsilon R. E means effective. Something similar to what we learned for a coaxial cable, but here is a little bit different. Why? Why? This is the most important part of the microstrip line. Let me draw a geometry, or maybe Wenshou can help us to draw the geometry of microstrip line because you have a gift. You want to draw, tell us what are those important geometry of the microstrip line to help yourself to realize, to understand the microstrip line and to draw it for the cross section. Yes. I think all of you familiar with microstrip line, right? Yes. A little bit small. We have a big whiteboard, right? Can you read? Chen Jai, can you read? Too small? No. Hey, you cannot read. You cannot see. Too small. Okay, let's take a rest and we can wait until you finish the dimension. Okay, let's take a rest. OK 了，帮忙画一下。